Given that we have seen a little bit what are the problems of randomized controlled trials when we don't do the proper randomization, I would like to discuss something that is called the false discovery rate. Is when we perform one test after the other. So these are features about our way we implement randomized controlled trials, and I want to go through the typical problems that we will incur by doing so. Okay. So we discussed one of the failures, which was this one of the problems, which is the failure to randomize properly. The previous video talks that if we pay attention to the observables, that gives some tranquility that what we're doing is correct. A second one that I have not discussed is the external and internal validity, is that how can you extrapolate the results of randomized controlled trials to the whole population. But the previous one will be a good indication of when you cannot do that. If the characteristics of the population that you are testing are different from the population in general, then for sure you cannot extrapolate. That would be the easiest way to understand that. There's something that happens a lot in the medicine and also in social sciences, but I think in social sciences we pay attention to it, is that by performing the test you are changing the behavior. So that's something that actually happens a lot. So if you want to solve, for example, sexual harassment in our organization and you want to test if a course, for example, a type of training will reduce hostility toward women in a particular company, well, the fact that you're running this and everybody knows that the management is concerned or at least paying attention to this will change the behavior even from the subjects that are not subject to the experiment. Just knowing that somebody else is running an experiment, it might actually change the behavior. That's, for example, when we do the placebo effect in medicine. That will be an example, okay? Now, the one that I want to talk about is when you do multiple testing. So we test multiple times with the one after the other, okay? So I want to show you first what are the features of estimation and what happens. You have heard me say that every time we estimate, that's a random variable, that there's a true beta in the population, and we get a version of that data. We don't get exactly the same one. That beta that we're obtaining is a random variable, and the reason why that is random is because we pick random subsamples from the data. So for example, imagine that I wanted to know the proportion of Latinos in the Sloan School. Well, one way to do that is I count all of them. So right now I take all the students that have been admitted, I count how many Latinos from the ones that are not Latinos, and then I compute that ratio. That would be the true proportion in the population, which is the current my MBA students. But I can also, instead of doing that, I can go to every classroom and just count how many Latin Americans are in that classroom. That of course, is an estimate, is an unbiased estimate of the true proportion, but every classroom will have a different proportion of Latin American. So therefore, there will be a distribution of the proportion of Latinos in each of the classrooms, and that implies that I don't get exactly the proportion, I get a distribution. So the reason why we get this randomness on the coefficients we estimate is that we have subsamples. So we don't have the full population, we just have samples. Okay, so I'm going to construct something that I will know everything. So we will have n observations of two types of individuals that have beta equal to 0 and individuals that have a beta equal to beta, okay? So I'm gonna, by the way, they're equal size, so there will be n individuals that are just a random variable and the expected value of the epsilon is 0, so we know it's constructed correctly. We're gonna construct a variable d that has a 0 for the ones that have no beta, 1 for the beta. So this is our experiment. And in the experiment, we know that for the individuals type D equal 1, there will be a higher value for Y. Is that okay? I'm going to put a lot of noise here to make things interesting and just to highlight. So the standard deviation of epsilon is going to be 1. So the epsilon is roughly between -2 and 2. And beta, when we put, we're going to try two different betas. We're going to try a beta equal to 0 and a beta equal to 0.25. So the beta is relatively small at a ratio of the total noise in the data. And what I want to do is to test. I just want to test what is the value of beta hat. And I'm going to estimate beta hat by saying what is the value of y conditional on d equal to 1 minus expected value of y, condition on d equal to 0, and I want to know what happens to that beta, okay? So I'm going to create 500 different tests. They are all identical in the sense that every one of them has half our zeros, half our betas, okay? So every time I do have a different draw of epsilons, of course, I create the dummy for all of those that are zeros and 1. I construct the variable y as I explained, and then I compute what is the beta hat from that regression, okay? And I just report that. I'm going to start with beta equal to 0, and I want to know how many times I reject the hypothesis beta equal to 0. So I hope that very few of them. Is that clear? Then when I try beta equal to 0.25, and I test the hypothesis is beta equal to 0, I hope that I get a lot of rejections, okay? So that's kind of the idea. Let's see if the test is relatively good. By the way, n is going to be 100. So we have about 200 sample in our data. Okay, so when I do the draw, this is the first beta, this is the second beta, this is the third beta, this is the fourth beta. So what am I showing here is that actually in the distribution, the betas are not all of them are 0. Even though I know that beta equals to 0, they are not 0. This is an estimate, and then they are just jumping all over the place. So every new random draw of epsilons, I get a different beta. In other words, this is how many Latin Americans you have in the classes. Well, it's just giving me different numbers depending to all the classes that I go. And as I go along, I will actually get more and more and more betas. And as you can see, the distribution is filling up. This is because all of the estimates that are taking place. When I finish that gives me a distribution of the coefficients, also give me a distribution of the t-statistics, how significant they are. And you can see that the density is around 0, okay? So that's good because I know that beta is equal to 0. But there are some betas that are very high in the extremes, as you can see here. Not only that, when you look at the t-statistics and you put 196, which will be about here, all to the left are non-rejections, so that's good. We are not rejecting their 0, and I know that it's not 0, but there are some rejections. So this is the data is telling me that the beta is different from 0 when that is actually not true. Okay? So these are bad inferences. By the way, if you do that with 0.25, you get, again, the data is around 0.25, so that's good, okay? But you have some that are actually negative and very low and some that are very high. And indeed here, you get 195, 196 is here. Notice that on the left, we get non-rejections. There are a lot of non-rejections, a lot. Now, of course, there's a lot of rejections, okay, that's good. So this is the good part. But there's a lot of non-rejections. So even though we know that the beta is 0.25, we get no. And again, I cook the example to get this very high proportion. In fact, actually, there's more non-rejections than rejections. So it's actually, this test is really bad. So, and the reason is a combination of the number of observations, 100, and the standard error. The standard error of epsilon is 1. And the beta is relatively small. So I have a lot of noise. So this is kind of the summary of what happens with those 500 draws. 4% of them, you get rejections, even though the truth is not, is that the beta is equal to 0. So we reject even though is equal to 0. And notice that a lot of times, even though the beta is different from 0, we do not find it significant. So these are, the ones in red are bad realizations. And in class, I want to talk a little bit about the interpretation of this. Let me discuss something that is called the confusion matrix. The confusion matrix is something that highlights the problems that we have said here. And there are different numbers or proportions that are relevant to pay attention. So in blue are all the good things, okay? In blue, this is rejection, so the test is significant when we know that the beta, in fact, you can think that this is the beta is equal to 0.25, and this is beta equal to 0. So we know that the beta is different from 0, and we reject it. So this is good. This blue here is also good. It says that I know that the beta is equal to 0, and then I do not reject. That's good, okay? Now you have the bad ones that we have been discussing. This is the V and the T, okay? The V is I reject, the test is significant, when actually in reality the data implied that the beta was 0. And these are the ones that I don't reject even though the person or the beta was 0.25. The other two other numbers that I want to pay attention, okay? One is the total number of tests. This is the total number of tests, okay? But this is the total amount of rejections from the test. So this is something that we observe perfectly. We know how many we test and how many rejections we got. Now we know that R will be equal to V plus S. So when we observe a rejection, we truly don't know how many of them are coming from V and how many are coming from S. And one non-observable, very important number is the M0. How many times do you think that your test should be rejected in the data? This is how many, what is the proportion, okay? So let me just give you the numbers from the exercise that we did. We are gonna come back to this in a second. So, but let's just put the numbers. What I got is 20 rejections when beta was 0. I got 213 rejections when beta was 0.25. That means from the total 233 rejections, 20 are incorrect rejections, things that I should have not rejected, okay? On the other hand, the M0, we know that in 500 of the instances, okay, the hypothesis that beta equal to 0 was true, we only reject 20. So look at the difference of these two numbers. One is called the false positive rate. That's the ratio between the 20 and the 500. We have a relatively good test. This is called the size of the test. The size of the test says that in 5%, typically we say 95% confidence interval, so 5% of the time you will make a mistake. So this is a test that is relatively good. On the other hand, the false discovery rate, in other words, when I see a rejection, okay, from the 233, actually I have a higher likelihood of making a bad decision, about 10%. So in other words, about 10% of the time I will be making a mistake. Just to give you an idea, this is a table for the experiment. In fact, I given you a software that you can change the n. This is the n, the size of the test, and this is the beta, okay? And this is how the test performs. Notice that when beta is big and when there's a lot of observations, we get a lot of ones, which is what you expect. So we always reject with a lot of data and with beta being far from 0. But when you have relatively small betas and relatively small samples, notice the tests are very, very bad. So even though we know it's different from 0, you can barely detect it, okay? And that implies that when you observe a rejection, it's very likely that the rejection is taking place not because truly the data is rejecting, it's because you just got a random drop that rejected that. When a company performs one test after the other, that's what is called the spaghetti testing, okay? Is that you just perform one test after the other without stopping. There's very famous examples in medicine. I'm going to actually use those. It's called spaghetti testing because what you do is people say that you know when the spaghetti is ready because you throw the spaghetti and sticks to the refrigerator, okay? That truly is not a test about when the spaghetti is done or not. That's a test that you are not Italian, okay? That's 0. You have 0 Italian heritage. We do not do that for testing the pasta, okay? But it's called spaghetti testing because the idea is that you throw a bunch of spaghettis to the refrigerator to see what sticks. See, that's actually the size of the test. If you take 100 tests and you throw them into the refrigerator, 5% of them will actually get stuck. This is very common in business applications because people now think that it's much easier to test. You have a lot of tools in Google, Amazon, and in all the networks, Twitter, etc. that allow you to do a lot of testing very fast. And the internet, you have a lot of testing all the time. And when you do all this testing continuously, you will find rejections that are truly not meaningful at all. You are going to be making a lot of mistakes, and a lot of those testings that you're going to be performing are just useless, and you're going to find something and act on something that was just noise, not knowledge. And that is, to me, the biggest cost that we have. I'm going to talk about the false discovery rate. In other words, when I discover something, when I find a rejection, what is the likelihood that what I found is truly a feature of the data, or is just a feature of the error? Okay, that's more or less the idea of the false discovery rate. So I'm going to give you this super famous example. You can find this even in Wikipedia. This is how they teach the doctors. So we're going to have a super good test, by the way. This is super good. We're going to test 10,000 people. And those 10,000 people, only 5% have a disease. So they have a particular gene or whatever. 95% are healthy. So so in other words, the 5%, the 95% represents the beta equal to 0 if you want, and the 5% represent the beta 0.25. So there's 5% of the population that have 0.25, 95% of the population has 0. Now we will have a very good test that if you are sick, it will detect you with 90% chance. That is a very good test. If I go back to the table I showed you, you will see that get to 0.90, you need either betas to be very different from 0, or you need a lot of observations. So that's a very good test, okay? Very high quality test. And second, this is the size, 2%. And the size means that when beta equals to 0, you will only reject 2% of the time. Is that clear? This one says that when beta equals to 0.25, you have 90% chance of rejection. This means that you only have 2% chance of rejection. So it's a very, very, very good test. So let's see what happens. So if I have 1,000 people, I know that 5% have disease, 95% have no disease. That means that 500 are here, 9,500 are there. Now, from the ones that have the disease, we know that with 90% chance you reject. So these are the rejections. So that's good. You are sick, and I find you are sick. Okay, 50 are we miss them, and from the 950, we know that 2% will found rejections. Again, the test is of relatively good quality, so that means that 190 are positive when they should not be. This is an incorrect inference. Is that okay? 9,300 will found negative. So I want to concentrate on these two places. So what this says is that in an extremely good test, okay, if there's a very few number of individuals that are sick, so in other words, here we have only 5%, okay? The problem is that you are going to find a lot of rejections when there are truly no rejections at all. In fact, in this example, about 30%. So when something is very unlikely to exist in the data, you will very likely find a rejection that is not meaningful. So in this case, 30%. And in fact, you can do this in our example. For example, if you go to our example of the 500, and let me assume that I perform 1,000 tests instead of 500, just for the sake of the argument. So imagine that in the sample, we have theta, which is the proportion of betas equal to 0.25. Let's assume there's only 1% of them, okay? And let's assume that 99% of the people have a beta equal to 0. And I am doing a random draw, and I just try to find the rejection. Look what happens. You get 40 rejections, that's the V. So these are 40 rejections when beta equals to 0, and only 4 rejections when the beta is equal to 0.25. So 90% of the chance you're making the wrong decision. Now, of course, this depends on the theta. When you increase the theta, let's say to 5%, so 5% of the people have 0.25, and 95% of people have only beta equal to 0, then still you get more rejections when beta equals to 0 than rejections when you get 0.25. So still you are rejecting more regularly than not for the wrong reasons. By the way, around 10% is when this shifts. This is my example. This depends on the example and depends on the test, on the quality of the test. Now, if the proportion of theta is large, let's say that theta is equal to 90, in other words, this is saying that 90% of the population has a beta of 0.25, then notice what happens. Now the test is very good because we reject 400% of the times, 400 times, sorry, we had 400 rejections and only 4 mistakes. That means that you only have about 1% bad decisions. This is how the false discovery rate changes with theta, and I want to say that this goes down very slowly. So you need a population to be a feature of the population, that 20% of the population has it. So we make 30% mistakes. That is a lot. That's a lot of mistakes for something that is very common in the society. I mean, this tells you that these tests are very bad. Performing one test after the other, you're going to find a lot of rejections that you should not act upon it. So this is what this is telling you. There are ways to correct for this. In fact, let me just tell you kind of the best ways to correct for this. The first one is to become Italian. So if you developed an Italian gene, and therefore now you will never perform the spaghetti test the way people do it. You don't throw things to see if they stick, and that gives the discipline to know how to do proper statistical testing. So my question to you is, do you like to watch games that end 0-0 in soccer and that you enjoy that? If you enjoy that, then you are totally Italian. Now, if you want to know if you're from the south of Italy, or especially from Napoli, then you just have to ask yourself if Maradona means something to you. Something good, like, God. But by the way, that will also be a test of Argentinian, okay? So Argentinian or from Napoli, Maradona means something. Now, if what you want is Baggio, Baresi, Totti, Dino Soft, then you're from the north. So you're Italian, but you're from the north. So that's kind of the test. Now, if you cannot develop an Italian gene, there's a second alternative to avoid this. And that starts with, do not work ever in McKinsey. If you work in McKinsey, then you're all the spaghetti testing all over the time. Now, there's a second alternative, which is not even have a summer internship in McKinsey. There's a third alternative, which is don't even apply for a job in McKinsey. Now, if you cannot develop the Italian gene, or you cannot help yourself, and you are actually applying for a job in McKinsey, then there are procedures to deal with this. And there are statistical procedures that are a little bit about beyond the scope of what we discuss in this course, but these are procedures that once you do the testing, it changes the size. So in one test, you reject with, let's say 5%. The second time you do a test, you now have to reject with 2.5, and then 1, and then 0.5, and so on. So you move the goalpost. By moving the post, what you're doing is making it harder to find a rejection. So you are truly sure that you're rejecting based on a feature of the data and not on the errors of the sampling. That's kind of it.
Poi Maradona, gol! Napoli! Una traversa, poi il traversone al centro, Maradona, il tiro, il gol. Rivale Maradona! Maradona, Diego Armando Maradona. Una grande cosa,
See you in the next video, and for all my paisanos, ciao.